Organic chemistry is often referred to as the chemistry of carbon. And this is for a simple reason. Almost all of the molecules that we'll encounter in organic chemistry will contain carbon. Carbon is a very unique atom. It can form a variety of different molecules, from things like diamonds, our hard units of bonded carbons, to very complex biological molecules like proteins, or of course gases like acetylene or methane, which we've talked about before. All of these are possible through the different chemical bonds that we can form with carbons. Now, as we know, carbon has 6 electrons. 4 of these are valence electrons that reside in its outer electron shell, while 2 of these are core electrons that are hidden in the inner shells of our carbon atom. We represent those 4 electrons on our Lewis structure as 4 little dots around that carbon, and each of these are going to be used to make bonds. Now, our general picture of bonding, of course, we're just forming bonds using electrons between our 2 atoms. So here we have 2 carbon atoms sharing 2 electrons to form a covalent bond. Now, since carbon has 4 valence electrons, we can share these and make 4 different bonds in order to bond many different carbons together, or of course bond carbons to other atoms as well. As we've seen before when we looked at reactivity, when we bond other atoms on here that might have varying electronegativity, like an oxygen atom, this will have a key effect on our reactivity by pulling our electrons towards our oxygen and creating an area of high electron density, or a nucleophilic area. Right? So this would become partially negatively charged as it's pulling those electrons toward itself, and this would then become that reactive site in our molecule. We of course talked about this in detail in our previous reactivity video, but for today what we're primarily interested in is how the bonding of our carbons can affect the structures of the molecules that we build. So we're going to remove this oxygen, and we're going to look at very simple structures with just carbons, and we'll add on hydrogens as well. So since we have carbons and hydrogens, we refer to these as hydrocarbons. So hydro, of course, refers to our hydrogens. Carbon refers to our carbons. Now, our hydrocarbons are going to be further broken down into several different classes based on the kinds of bonds that we have between our carbons and hydrogens. We have alkanes, alkenes, alkynes, and arenes. These are all different classes of hydrocarbons. We also refer to these as functional groups because they'll change up how our molecules function as we add these different classes of hydrocarbons within our molecules. Okay, so let's take a closer look. So these are all going to be hydrocarbons, so they'll just contain carbons and hydrogens. And we're going to need to take a closer look at their bonding in order to understand what's different between these 4 different classes of hydrocarbons. So we're going to start with our simplest class of hydrocarbons, which is alkanes. So alkanes, of course, consist of carbons bonded to hydrogens with single bonds only between our carbons and hydrogens. Now remember, of course, a single bond forms when we share 2 electrons. And we can also create double or triple bonds by sharing more electrons between our carbons. But we want to take a closer look at this bonding here as well using our valence bonding model. So in our valence bonding model, we need to look at both the numbers of electrons that are bonding together, but also what orbitals those electrons are in. And we want to look at overlap of orbitals as forming our bonds. All right, so let's take a look at a carbon atom. So as we know, our carbon atom has 4 valence electrons, 6 electrons overall. Now, if we want to look at our electron configuration for a carbon atom, we can actually see where those electrons are in our given orbitals. So in our first electron shell, remember we have a 1s orbital. That s refers to the fact that we have a spherical orbital. So it's just a little sphere as our lowest energy level orbital. And we write a little 2 up here indicating that we put 2 electrons into that little spherical orbital. That fills up our full first shell. So then we move up to our second shell of electrons. These are our valence electrons for carbon. At the second shell, remember we have 2 different kinds of orbitals. So we have another s orbital. This is going to be a larger s orbital, the 2s orbital. But then we also have a different shape of orbital, a 2p orbital. So our p orbitals, we have kind of this dumbbell shape where we have 1 lobe on the top and 1 lobe on the bottom. And we have this node in the middle between those 2 different lobes. Now our p orbitals, so that p of course tells us that we have a different shape. But now that we have this directed orbital, we can also change the orientation of that orbital, and we actually have 3 different p orbitals. So remember we have 2px, 2py, and 2pz. And each of these just represent orbitals pointing in different directions. The z orbital will be pointing straight towards the camera and straight back towards me. I'm going to draw that like this. The dotted one is pointing away from me and towards the camera. And this other one I'll kind of shade in as the bold one is going to be pointing straight out towards me and straight away from you guys watching. So there's 3 different orientations of this orbital to make 3 different unique orbitals that we can put our electrons into. So with our 4 valence electrons, we want to use our off-ball principle to develop our electron configuration. So we put them in the lowest energy orbital first, which is our s orbital. This requires less energy than our p orbitals. And then we can split up our other 2 electrons between any 2 of our p orbitals. And it doesn't really matter what p orbitals I put those into. So that's the picture of my carbon atom, right? I have these electrons sitting in these specific orbitals around my carbon atom. Now, as I said, bonds are formed by orbital overlap in our valence bonding model. So if we have 2 carbon atoms bonding together, like I'm showing here, we have to have different orbitals overlapping between these carbons. So if I draw my carbon, I'm just going to show the 2 orbitals. So here's my 2s orbital, and now here's my p orbitals. There's 1, there's 2, and then of course I've got the 3rd one that's sticking straight out in front and straight out to the back. So there's my 3 different orbitals, and I'll just put I have 1 electron in this orbital. I'll say I've got 2 electrons in this orbital, 1 electron, oops, I already have an electron in that orbital, let's put it up here. Okay, so there's my carbon atom with my different orbitals. Now let's bring another carbon atom over here and try to form our bonds. So I bring in my carbon atom. Here's another carbon. And okay, I can overlap 2 p orbitals together and make a bond. So that looks fine. That looks just like what I have up here. My little arrows here are representing the individual electrons in my orbitals. I have 2 orbitals. I have this little overlap right here between my orbitals. And so that's representing my chemical bond that I have right here. So this is the chemical bond. We refer to this as a sigma bond. A sigma bond forms when you have a symmetrical bond from two things overlapping head-on. So this is head-to-head overlap. Now, let's say I want to add on one of my hydrogens that I have shown here bonding. Now, hydrogens only have one electron. It sits in that 1s orbital, right? Because the electron always goes to the lowest energy orbital first. So I add on my hydrogen here. It's got a little spherical 1s orbital surrounding it. And I'll put my little arrow representing the electron in there. So again, we can form a bond. Everything looks okay so far. But now let's think about what's going on with our bonds here. So if we look at our two bonds, they're exactly 90 degrees away from each other in terms of our angle. Right? This is an angle of 90 degrees here. We have a 90-degree angle between our two bonds. Right? There's 90 degrees between each of our three p orbitals. Now, of course, up here it looks like 90 degrees too, but if we remember back to our valence shell electron pair repulsion theory in general chemistry, we know that these electrons, they're all negatively charged, so they're going to be pushing away from each other. Right? We have two electrons here and two electrons up here in each of these chemical bonds, and they're both pushing each other apart. Right? They're repelled by that like negative charge. So because of that, our bonds get pushed apart and we get these 3D tetrahedral shapes for our carbon atoms. Right? Each of our four bonds push each other as far away from each other as possible, and that gives us that tetrahedral shape. Right? So in general chemistry, we represent that like this. So we show our carbon atom. There's one bond to a hydrogen. Here's my bond coming over here to my carbon. Notice I have this larger angle here. This comes out to a 109.5 degree angle. That's the ideal angle for our tetrahedron. And then we use wedges and dashes to represent the other bonds over here. Right, so this dash is a bond going towards you guys. This wedge is a bond coming out towards me. And we have a 109.5 degree angle between each of our carbons, each of our bonds to that carbon. Now, if I look over here, my orbitals can't overlap in that correct tetrahedral shape. Right? My p orbitals are always 90 degrees relative to each other. I have this s orbital that's just kind of sitting in the middle here. I can't really get those different angles with these current orbitals here. So we need new orbitals if we're going to be able to form this sort of shape over here. So this is where we get our concept of hybrid orbitals, which of course you learn in general chemistry as well. We're actually going to take our orbitals and we're going to mix them all together and then pull them out and make new hybrid orbitals that we can orient around our carbon in this correct tetrahedral shape. So we take these four orbitals that we have for our carbon, and we're going to smash them all together. So we have one part of S, so we have one part S, and then we have three parts P stuck in here as well. So we have an S, a P, and a P all mixed together to make a new hybrid orbitals. So we refer to this as sp3, right? Because it's one s orbital and three p orbitals mixed together. We smash them together in a big black box. All right, so they're all mixed together, and then we break them out to form four new hybrid orbitals. And these are all going to be the same sp3 orbitals. They're going to look kind of like p orbitals, where they have two different lobes, but they're also going to be kind of like s orbitals. So they're going to have one big lobe and one little lobe. So we mash all these orbitals together, make our new sp3 orbitals, and now these we can arrange around our carbon in the correct tetrahedral shape. So now I have my carbon, I can redraw my sp3 orbitals. I'm just going to show the big lobe for these. I'll again use a little bold to represent this coming out towards me, and use dashes to represent that's going away from me. I have my 4 sp3 orbitals. I can put one of my valence electrons in each. Again, I have my little arrows representing electrons. And now I can easily make my 4 bonds that I have represented in my alkane here. So I put my hydrogen up top. It still has a s orbital. We can get an overlap between our 2 orbitals. This is a head-to-head overlap, so it's another sigma bond. Put my other hydrogens on. And of course I have my other carbon down here, which is going to be using another sp3 orbital to bond to my first carbon over here. So each of them have our shared pair of electrons forming that covalent bond. They're all the head of an sp3 orbital intersecting with either an s orbital or an sp3 orbital. These are all what we call those sigma bonds with that head-to-head overlap. Spherical orbitals like s orbitals are always making sigma bonds because basically everything on our spherical orbital is the head. So it's always head-to-head. So here now we have our picture of our carbon bonding for our alkanes. Right, so we're forming these hybrid sp3 orbitals. Right, that's just named from the fact that we have one s orbital and 3 p orbitals getting mixed together. We use that to make our 4 different bonds, each at that tetrahedral 109.5 degree angle. And this basic chemical structure will be repeated for all of our alkanes. Right, so our alkanes always have these single bonds, which are also going to be sp3, and they're also sigma bonds. And those are shared characteristics for all of our alkanes. Now let's take a look at our next hydrocarbon class, which is alkenes. So alkenes are characterized by double bonds between our carbons. Double bonds, that's the first key characteristic of our alkenes. Now, if we look at that from our normal Lewis structure perspective, so we'd have our carbons, and we're going to be sharing 2 electrons from each of our carbons in this double bond. So we have 4 electrons here total. So that takes up 2 electrons from each, and then we'll end up with our other 2 electrons could be forming bonds with other hydrogens or other carbons as well. So this is the basic picture of what an alkene would look like. We need to have that double bond between our carbons. Now again, if we go back to our actual orbitals, we're going to need to make hybrid orbitals in order to form our bonds between our carbons and our hydrogens, right? So if we go back to our valence shell electron pair repulsion theory, again, we know that our electrons here are repelling each other, and in order to get the maximum separation between each of our groups of bonded electrons, we get a 120 degree angle or a trigonal planar shape. Right? So we actually have this flat shape where each of our bonds are pointed as far away from each other, are pointed out at 120 degree angles from each other to maximize the distance between our electrons. So that's what our shape is going to look like. Now how can we make that shape using our orbitals? Now what we're going to do here is, since we're only bonding with 3 different atoms here, we're actually just going to take 3 of our orbitals and smash them together to make our hybrid orbitals. So we're going to do our same hybridization, grab 3 of those orbitals, smash them into a box. So now we're taking an S, a P, and a P, and we're going to use those to make our 3 bonds at 120-degree angles. SPP, well that would mean SP2, right? The 2 is indicating that we're mixing 2 p orbitals together along with our 1s orbital to make these new orbitals. And they're going to look similar to our sp3 orbitals, right? It's still going to be kind of that same general thing of a big lobe and a small lobe, sort of like a p orbital, but then that asymmetric shape is due to that s characteristic that we're adding in there as well. So now I can draw my carbon out, and again I'm going to show the big lobes of my sp2 orbitals coming out, and I can show my other atoms and my orbital overlaps to form my bonds. As before, these are all overlapping head to head, so that means that they are going to be sigma bonds. So I have 3 sigma bonds. Now, as we look at this structure, so we're obviously missing something here, right? So I only have 2 electrons that I'm showing here overlapping between my 2 carbon atoms. But as we know, this is a double bond, and I should have 4 electrons. Where is my other bond? Where are my other 2 electrons? Well, in order to show that other bond, I need to think about where my last electron is, right? So I had my 3 sp2 orbitals, each with 1 electron, and there was 1 orbital that I didn't use when I was making my hybrid orbitals. I have my 2p orbital over here. Let's remember it's going to be sticking straight out towards me, and then straight out back towards you guys. And I would also have my other carbon with that same kind of shape. My orbitals sticking straight to the front, straight to the back. And I have 1 electron in here, and 1 electron in there, in my p orbitals. Now these orbitals, of course, they aren't pointed towards each other, so we can't have that head-on sigma bonding overlap. But when they're sitting side to side like this, we can actually have a little bit of overlap between these orbitals that are sitting side to side. So you get this side to side overlap. And we call this a pi bond. So our double bond actually consists of 2 different bonds. 1 sigma bond formed by my sp2 orbitals, and 1 pi bond formed by these p orbitals overlapping by sitting right next to each other. Right? So they're both pointed in exactly the same direction. Right? They're pointed out towards you guys and back towards me. So they're both sitting next to each other, and then they're able to overlap somewhat side to side. So of course in my drawing here you can't really see that overlap very clearly, but in reality these would be much bigger around, and you'd be able to get some side-on overlap between these orbitals sitting next to each other. So going back to my overall picture here for my alkenes, so they have the same atoms here as my alkanes, right? It's still hydrocarbons, hydrogens and carbons, but now I have double bonds here. And I have then sp2 orbitals. So the sp2 orbitals are overlapping. They're getting my 120-degree angles and my sigma bonds. So I do still have sigma bonds, but now I also have a pi bond here as well. And this unique bonding changes the structure and the shape of my molecule, and will then also change how it behaves. Now for my 3rd class of hydrocarbons, I have alkynes. alkynes are unique in that they have triple bonds between our carbons. So again, with my valence structure, I would show my two carbons triple bonded together. I would then have bonds sticking out to either side, which could be to hydrogens or to other carbons as well. Now in this case, so I have, of course, 3 of my electrons from each carbon being shared in my triple bond. So this makes 6 electrons altogether, shared in that triple bond. And then of course I have my normal single bonds to my hydrogens. Now again, as my bonds repel each other, they're going to push each other as far away from each other as possible. When I only have 2 different bonds here, this is going to be a 180-degree angle. So I get this linear structure where I put them as far away from each other as they can on opposite sides of my molecule, or opposite sides of my atom there. Now again, we can follow the same reasoning that we had before when we made our hybrid orbitals, where we only need to mix as many orbitals as we need to form those 2 different bonds to our groups on either side. So we grab one p orbital and one s orbital, we mix them together in our black box, and we're going to get out a new orbital. Again, it looks very similar to our sp2 and sp3 orbitals. In this case, we're just mixing one s and one p, so we get an sp orbital. So my carbon will have my sp orbitals sticking out one on either side. I have my hydrogen and my carbon. I've got my overlap creating, again, 2 sigma bonds. All right, so it's head-on overlap, sigma bond, sigma bond. Now, as we had with our alkenes, with our double bond, we had our extra p orbitals coming in here to form our remaining bonds to make up that double bond, or in this case, our triple bond. So we still have our p orbitals. I'll go with one sticking straight up and down, and then I have another one coming out towards me and back towards you guys. I'll draw the same thing over on my other carbon. There's the sp. Here's the one coming out towards me, going back towards you guys, and then the one on top as well. I'll just go ahead and fill in my hydrogen also. And I've got my electrons. 1 electron in each p orbital, and 1 electron in each sp orbital. Now I have 2 p orbitals that each have their electron on each of my carbons, and both of these sets of p orbitals can overlap in the side-to-side pi bonding. Right, so the sides of my orbitals can overlap, and I actually get 2 different pi bonds to make up my full triple bond. So note, if we count them, we have 1, 2, 3, 4, 5, 6 electrons all overlapping together to make my 6 electron triple bond. So again, we can summarize this. Our triple bond results in sp orbitals, and we have those sp orbitals participating in sigma bonds. We also have our p orbitals that were left over that are being used to make 2 pi bonds. So we have 2 pi bonds now to form our triple bond overall. And this will be the main characteristics of our alkynes, resulting in a unique structure compared to our alkenes and alkanes. Now we can have different combinations of alkanes, alkenes, and alkynes together. So we might have one molecule with triple bond in one place, and then single bonds between carbons in other places, in which case we'll just have the same kind of structures, just in different regions of our molecule. So again, that's why we call these functional groups, because they can just be one functional part that will have common characteristics at one point of our molecule, and then you might have another functional group at another point of our molecule. So for example, if I change this to a carbon, I could have another carbon over here that's just following my typical alkane bonding. So this would be sp3 hybridized with my 4 bonds going out at 109.5 degree angles. I have my triple bond over here that's sp hybridized. I could have another carbon over here on the left and make this one sp2 hybridized if I have a double bond. So here's my 120 degree angles, and with my double bond between my carbons over here. Both of these, since they have double bonds, would be sp2 hybridized. The general rule is that if our carbon has 4 bonds, is bonded to 4 different things, it's going to be sp3 hybridized. If it's bonded to 2 different things, it's going to be sp hybridized. And if it's bonded to 3 different things, it's going to be sp2 hybridized. Alright, so the number of letters or orbitals that we combine together to make those hybrid orbitals is going to be equal to the number of different things that we're bonded to. Our last class of hydrocarbons that we'll look at is arenes. So arenes are a little bit about a special class where we have both carbon-carbon single bonds as well as carbon-carbon double bonds. They're usually going to form these ring-shaped structures, such as what I just drew here. So where we have an alternating sequence of single and double bonds between our carbons moving around connected together in this ring. We would also, of course, usually have hydrogens connected on here. So each of our carbons has 4 bonds. And we get our full structure here for a simple arene. This is benzene. Here, of course, we're going to have the same kind of characteristics that we had for our previous alkanes and alkenes. So this would have 3 different groups bonded to it. It would be sp2 hybridized. We go around the ring, and we actually see that each of these is going to be sp2 hybridized since they each have a double bond that they're using. Right? They each have a double bond that requires sp2 hybridization, and they have 3 different groups that they're bonded to, 3 different atoms. So arenes are simply a special case, kind of a mixture of alkanes and alkenes. This kind of shows us how you can use multiple different kinds of bonding. You can build it together into a larger molecule. And that's what we'll see throughout organic chemistry. We'll see these same kind of structural principles applied in different areas of a molecule, and then those will work together to make a functional whole for that molecule. Right? So you can have one molecule that has alkene, carbon-carbon double bond bonding in one area, and then maybe carbon-carbon single or alkene bonding in another area. And together those will work together to make our molecule. As we'll see later, the kinds of bonding that we have, whether it's the pi bonding or the sigma bonding, the different hybridization, sp2 or sp3 or sp, that will affect how our molecule behaves, and will actually change the reactivity slightly. So these different classes of hydrocarbons do end up behaving slightly differently, even though they're all just made of carbons and hydrogens. It's one of the amazing things about organic chemistry. Just small changes in how our atoms are bonded together, even without changing the kinds of atoms that we have, can have large effects on our overall molecule's behavior.